In the last video, we looked at how we might be able to classify different differential equations in differential form and see whether they are separable, linear, or exact, the three methods that we just learned. Now, in this video, let's think about, alright, if we have an equation, let's just determine whether it's exact or not, and then, if it is, let's solve it. So, I don't think it would be very useful to show you an equation and then go through the steps to show it's not exact, so I have taken the liberty of finding an equation from the textbook, which is indeed exact. It is question 10 from section 2.4. And the differential equation that it gives us is 2x plus y dy, 2x plus y dx, excuse me, plus, and then x minus 2y dy equals 0. Now, even though you're holding in the back of your mind, I told you this is exact. How do we know it's exact? Let's find out. This here is our function p of xy. This is our function q of xy. Let's see if their mixed partials are equal, in which case we'll have a function, and then we can go ahead and solve it. Alright, is the partial of p with respect to y equal to the partial of q with respect to x? Let's see. Alright, the partial of p with respect to y. 2x disappears, y becomes 1. The partial of q with respect to x, negative 2y disappears, x becomes 1. So indeed, the partial of p with respect to y equals the partial of q with respect to x, and this tells us that our equation is exact. It is exact. Because it is exact, we can now apply the method that we came up with 2 videos ago to solving this differential equation. Now, because we know that our equation is exact, it tells us that there must be some function, f of x, y, who has the following properties, or which has the following properties, which has that the partial of f with respect to x is 2x plus y, and the partial of f with respect to y equals x minus 2y. I know it's already much easier when we're just plugging things in, isn't it? Alright, so now we can actually pick either of these two constraints as our starting point and use the other one to solve for our function of integration. But let's just keep it simple and use f sub x. So, what do I mean? Let's say that the integral of f sub x equals the integral of 2x plus y, and this is going to be partial x. And again, we're going to have some kind of function of integration, which is going to be some function purely of y, because when we take the partial derivative with respect to x, not only do constants disappear, but also any pure function of y. So the sine of 12,000y plus 16, that'll also disappear when we take the partial with respect to x. So we need an entire function of just y. Okay, if we take this, then what we're going to get is that our function, f of xy, we're making progress. We have an expression for the function. The expression for the function is that we have this integral. So what is this? Okay, integral of 2x plus y dx. So 2x, partial x, the integral of that is going to be x squared, or 2x squared over 2, which is just x squared. And the integral of y dx is going to be xy. And again, we still have plus our function of integration, h of y. But this is good. We already have an incomplete expression for f of xy. Now, what we can do is we can use our other constraint, which is that the partial of f with respect to y equals x minus 2y. We can use that constraint to solve for h of y. Alright, how do we do that? What we're going to do is we're going to take the partial derivative with respect to y of both sides, which is going to be useful because it gives us some nice stuff. It's going to give us that on the left side, the partial of f with respect to y, which we can also just replace. We know that the partial of f with respect to xy is x minus 2y. So, okay, we have x minus 2y on the left side. So the partial of f with respect to y on the left. On the right, we're taking the partial derivative with respect to y of everything. So when we take the partial derivative with respect to y of x squared, we get 0, so we needn't include it. And then when we take the partial derivative with respect to y of xy, the y goes away and we're left with x. So x minus 2y equals x plus, and now we have our function of integration, not constant of integration, but a function of integration, and it's a variable y, so when we take it partial y, derivative with respect to y, we're just going to get h prime of y. And now we're getting really close, because as we can see, we can get rid of these x's here, they cancel out, and we're left with h prime of y equals negative 2y. It's amazing. It's much, much simpler to do an exact differential equations problem with actual concrete numbers than it is throwing around partials left and right. Alright, now if we use this, we can integrate with respect to y, and we get that h of y equals negative 2y squared over 2 is just negative y squared. And you might think, okay, do I need a constant of integration? Well, it turns out you actually don't. Because if you remember, if we put on this constant of integration, like not C2, C1 here, what would happen is when we replaced h of y, this h of y would turn into negative y squared plus C1. But if you recall, when we're solving the differential equation, ultimately we're setting this equal to a constant. So this arbitrary constant here, it won't matter. So just for the sake of showing you that, I'm going to include it, but we'll see why you don't need to include it for solving your function of integration in the future. So now, if we remember our fact about the total differential of x, it was that the total differential of x, df, was the partial of f with respect to x, dx, plus the partial of f with respect to y, dy, which was just our differential equation, and our differential equation equals 0, and this told us that df equals 0, and if df equals 0, the only way this is possible is if our function, f of xy, actually equaled a constant. So if f of xy equals a constant, well, we know what f of xy is now. We can plug it all in. F of xy equals, so f of xy equals x squared plus xy plus our function of integration, which we solve for as minus y squared plus c1. This is just going to equal some constant called c2. And now you see why the constant isn't really useful, because again, two arbitrary constants, you can just morph them into yet another arbitrary constant. So we're left with f of xy shouldn't be part of the answer because we're solving the differential equation. We're left with the solution to our differential equation is implicitly defined by the relationship between x and y, that x squared plus xy minus y squared equals yet another constant, c3. And this is the final implicit solution to the differential equation. You can implicitly differentiate. You know what? Let's actually do that. Let's implicitly differentiate this with respect to x, just to see if we can get back to our original differential equation to prove that this is actually a solution. So this is, we're going to verify, and this is our little checkbox to see, is it an actual solution? So this is our guess, but it's a pretty good guess because it'll be correct, because exact differential equations do work. Math isn't wrong, which is, it's nice. So let's verify this though. Let's differentiate it with respect to x. So we get that dx of x squared plus xy minus y squared equals, all right, well, the derivative of a constant is 0. So implicit differentiation, derivative with respect to x of x squared is 2x plus, and now this is a product rule, because again, this is x times hide and seek, x times y of x. Y is a function of x. So first, we have x is getting differentiated, and we just have y. And then we have another term where x stays as it is, and we differentiate y, so we get y prime. Or we can rewrite this also as dy dx, which is going to be useful because we're going to try to get this into differential form. And then here we have minus, again, hide and seek, y of x squared, even though we're not writing the x. So we have minus y of x squared becomes, if we use the product rule, sorry, not the product rule, the power rule, becomes minus 2y, and then again the chain rule times dy dx, derivative of the inside. This all equals 0. Now if we factor out the dy dx, we get, let's switch colors to ease the monotony. We get that dy dx times, and then we take this out, factor, so x minus 2y, we get that this equals, and if we subtract, well, okay, we don't actually have to subtract to their side. Let's just keep it on the same side, because we're going to get it into differential form anyway. Plus 2x plus y, that all equals 0. Now, if we simply multiply by dx, and I suppose also maybe reverse the order of this, then what we get is finally this implies that, so we're going to take the dx term first, so 2x plus y times dx plus x minus 2y times dy equals 0. This is the result. Again, this is just the first series of videos we did. We're just verifying, is this the initial differential equation? 2x plus y dx plus x minus 2y dy. We look up 2x plus y dx plus x minus 2y dy equals 0. This is indeed the differential equation that we began with, so we can give ourselves a nice check mark in the verification box. This is the solution, and now you know how to solve exact differential equations. All you want to do is verify it's exact first. That's always the first step. So always your first step is not verify solution, but verify that it is exact. So make sure before you're going to apply the methods that only work for exact equations, verify that it is actually exact. And then your second step is what we're doing right here, is solve for f of xy. Solve for that elusive function that we know must exist because it is exact. And then step 3 is just to set f of xy equal to a constant. And then optional step 4 is to verify that this implicit solution is indeed a solution. In our case, it is because we didn't make any careless errors. Good job. Okay, now you know how to solve exact differential equations, and it is indeed much, much simpler when it's concrete than when it's abstract.